Okay, this is Project Test 3, Video 1, and it's problems 1 to 10. Um, heights in inches for the 200 graduating seniors from Washington High School are summarized in the frequency table below. What following statements about the median is true? I want to go ahead and add an extra column and call it the cumulative frequency. So the C frequency for cumulative frequency. And we start off at 22. And then if I take 22 and I add 84 to it, this cumulative, because all I did was add these two together. If I add 62 to that, I get 168. Add another 24 to that, I get to 192. And then the total cumulative is 200. And that's all I did was make a cumulative frequency. All right, which of the about the median is true? Well, first off, we have 200 graduating seniors. So what is our median? Well, 200 divided by 2 tells me the median occurs at 100. All right, so as soon as we get to 100, we've reached the median. It is greater than or equal to 78. Well, maybe. We know it's greater than, that it's equal to 100, so maybe we can say that. That's kind of a possibility, but it's not equal to 78. We know it's actually going to be equal to right here, because this is where we hit 100. So it's going to be equal to 84. So it's definitely greater than 78, but it's not equal to 78. So I don't really like that, but maybe. It's greater than or equal to 72, but less than 78. No, definitely not less than 78. Oh, I'm sorry, I read this wrong. It's in the 60 to 66. So it's definitely not this. It's greater than or equal to 66, but less than 72. No, we're in the 60 to less than 66. It's greater than or equal to 60, but less than 66. And yes, that is what we found, is we are in this range. So the answer to number 1 is D. All right, because we're between 60 and 66 inches. And it happened because we needed to get over 100. Well, 22 is not over 100. Here this is our first value that crossed 100, and we know our median's at 100 because 200 divided by 2 is 100. So our median occurred at the 100th value. So our cumulative frequency of 106, that's it occurred here, and we had right here that size is 60 to 66 inches. All right, here we have 3 box plots, and Professor James gave the same test to his 3 sections of statistics on the 35 question test. The highest score was a 32. Well, that appears like that occurred here. And the lowest score was a 15, which also appears to be in the same class period. Based on the information below, displayed in the box plots above, which of the following statements is true? Section 1 has the smallest interquartile range. Well, this is my IQR, the box part, and clearly this IQR is larger than this one. It looks like section 2 has the smallest. So this would be section 2, not section 1, that has the smallest. So that's false. The lowest score in section 2 is higher than a highest score in either of the other sections. Well, the lowest score in section 2 is right here, and it is the lowest score of all scores, so no, that is false. Section 2 has the smallest range of scores. Well, it looks like this value right here was a 32, this value was a 15, and we can see that it has the highest score and the lowest score, so it has the largest range, because range is largest minus smallest. The top 25% of the scores in section 2, so this is the top 25% of the scores, are lower than the highest score in section 3, and that's not true, because the highest score is higher than this score, so that's not true. Not all of the top 25% are lower than this. Looks like this one might be, but not all of them, so that's false. So at least 50% of the scores in section 3, okay, so we're talking at the median right here, are higher than all of the scores in section 1. And when I look at this line, it's like, you know what, that's not a perfectly straight line, but it does look like this 50% value are higher than all of the scores. So 2E is our best answer. Okay, number 3. A well-designed experiment should have which of the following characteristics? Subjects have to be randomly assigned to treatments. Yes. Random assignment, and by the way, that is a term that we use for experiments. We use random selection for observational studies and random assignment for experiments. A control group or at least 2 treatment groups. The main thing that they're saying here is we have to have something to compare to. So either we're going to have 2 treatment groups or a treatment group and a control group. So you're going to have something to compare to. You have to have 2 groups that are receiving treatments, one of which might be a placebo. So that's true. Replication, have to have it. Okay, so consequently, you're going to have multiple subjects receiving the same treatment to identify variation, because we know that there are going to be some variables that we're unable to control for. So in this case, 1, 2, and 3 are true. E is our best choice. Number 4. The distribution of colors of candy in a bag are as follows. If 2 candies are randomly drawn from the bag with a replacement, what's the probability that they have the same color? Well, what's the probability of getting 2 browns? Well, the probability of getting 2 browns would be 0.3 times 0.3. That's the probability of getting 2 browns. What's the probability of getting 2 reds? 0.2. And then 0.2, and 0.2, and 0.2 for the greens. And then 0.1 times 0.1 for the oranges. Now, the fact of the matter is, if I'm only drawing 2 candies, I can get 2 browns or I can get 2 reds, but I can't get 2 browns and 2 reds at the same time. As a result, I can add them directly because I'm only drawing 2 candies. So I could get this, or I could get this, or I could get this, or this, or this. So let's add up those probabilities. So essentially it's 0.3 squared plus 0.2 squared plus 0.2 squared plus 0.2 squared plus 0.1 squared. And I end up getting 0.22 for my answer. So B, for number 4. Number 5. And by the way, generally speaking, when they give you a table, you should be totaling them up if they haven't done so. And this is one of those cases where they didn't do so. So we're probably going to need to come back and do a total. That's just a good hint. All right, that's a good way to think of things when we're working problems. So each of 133 children in the sample. So I'm going to guess that when I add all this up, the total of everything is going to be 133. In the sample, we're asked to choose a pencil. 3 different colors were available: yellow, red, and blue. The number of 2-year-olds and 3-year-olds who selected each color is shown in the table above. In a test of independence of color, which of the following is used as the expected count for 2-year-olds who select a yellow color? So we want the expected value. Well, remember, our expected value formula is just simply N times P, where N is the number and P is the probability. So we need to figure out the probability of getting a 2-year-old and the probability of getting a yellow. Let's go ahead and add these up. So 14 and 28 sum to 42. And 32 plus 24 is going to sum up to 56. And then we have 19 plus 16 and that sums up to 35. Now let's check this out real quickly, make sure those sum up correctly. So we should have 42 plus 56 plus 35. And sure enough, that checks up to 133. So we've added these up, so we've got these right. Then we're going to add this way. And we have 14 plus 32 plus 19 is 65. And continuing with the totals, 28 plus 24 plus 16 equals 68. And 68 plus 65 does equals 133. So it looks like we've added everything up correctly. That's really important. Well, what we're interested in are 2-year-olds and yellow pencils. So this is what I'm interested in. So if I were to do that, I would want to go 65 times 133 times 42 over 133, and that would give me my probability. So now I have my probability, but I need to get my expected value, which means I need to multiply by the number, which is times 133. So this is going to drop out. Okay, so we end up that we're dividing by 133. And it happens to be that we know that the yellow pencils are 14 plus 28. 14 plus 28, that was the yellow pencil. We happen to know that 14 plus 32 plus 19, which is right here, gives us the number of 2-year-olds. So E is my answer, okay? Number 6, approximately 52% of all recent birthdays were boys. In a simple random sample of 100 births, 49 were boys and 51 were girls. This is most likely an explanation of the difference between observed results and expected is what? Well, first off, we have a simple random sample. If we took a simple random sample, then it's not going to be biased. So that gets rid of that. Okay. Now, what we were expecting, the true population is 0.52. But we basically got a p-hat or a sample of 49 over 100 or 0.49. Well, how did that happen? Well, remember, every sample varies. So this is a case of sampling error because it didn't exactly equal what it's supposed to. This is just an estimate of that. This is sampling error or sampling variability. We did everything correctly, but because we did not take the entire population, we have a little bit of variability. It's just plain variability due to sampling or sampling error, as the case may be. Number 7, each person in a random sample of adults was asked how many DVDs he or she owned. Summary statistics are given below. Which of the following statements are true? The first thing, 75% of the adults in the sample own more than 95 DVDs. And it's like, no. Q3 says 75% own 95 or less, not 95 or more. So this is the wrong definition of Q3. Q3 is here. That is 75%, but 75% own less than that. 50% of the adults in the sample own between 0 and 129.4. That's because they're pointing to the mean. That should have been the median. So this should have been 50 DVDs for the median, not that's the definition of the median, not the mean. Be careful of that. Don't get caught. The distribution of the DVDs appears to be approximately symmetric. If they were symmetric, the mean and the median would be equal. Because they are not equal, this does not appear to be symmetric. That's the very first thing I would check, and they're not equal, so not symmetric. The interquartile range of the DVDs owned is 65. Well, IQR equals Q3 minus Q1. So 95 minus 30, which equals 65. So this looks pretty good. This looks like this is my answer, but I still want to go check the last one. The distribution of the number of DVD zones contains outliers on both the low and the high side. Well, so I need to go back and consider my outlier formulas. So for it to be an outlier on the upper side, X has to be greater than Q3 plus 1.5 IQR. And we already calculated an IQR of 65. And so we have Q3 is 95, 95 plus 1.5 times 65. So let's do that real quickly. 95 plus 1.5 times 65. So we need more than 192.5. So X has to be greater than 192.5. And sure enough, the maximum is 3,000. So we definitely have an outlier on the high side. So we have an outlier on the high side. What about the low side? Well, to be on the low side, X has to be less than Q1 minus 1.5 IQR. Q1, our lower quartile, was 30. So 30 minus 1.5 times IQR, once again, is 65. So 30 minus 1.5 times 65. And we end up with a negative. Well, there is no, can't have negative DVDs. So consequently, there's none on the lower side. So this is false. So there's an outlier on the higher side, but none on the low side. And the only answer is the IQR answer, which is D. For flights from a particular airport in January, there's a 30% chance of flight being delayed because of icy weather. If a flight is delayed because of icy weather, there's a 10% chance. So let's start circling these numbers. There's a 10% chance it'll also be delayed because of a mechanical problem. If the flight is not delayed because of icy weather, there's a 5% chance it will be delayed because of a mechanical problem. If one flight is selected at random from the airport, what's the probability that it'll have at least one of the two types of delays? The fact that I have two things going on probably means I need to make some sort of sample space table. And whenever I go about making a table, I look for a number that is only associated with one variable. And here I have a couple of variables. So I have mechanical delays and I have icy delays. So there is a 30% chance the flight is being delayed because of icy weather. That doesn't have anything to do with the mechanical, so this is only associated with one variable. So this is probably my one variable response. And then it says, if a flight is delayed because of icy, there is a 10% chance it'll be delayed because of mechanical. Ooh, that one has two variables. If a flight is not delayed, so conditioned on the fact that it's not delayed because of icy, there's a 5% chance that it'll be delayed because of mechanical. Once again, two variables. As a result, I sit there and go, okay, the only one that's one variable is 30%. So I'm going to go ahead and make my little table. And ice delay, no ice delay. Mechanical delay, no mechanical delay. Just because I like to keep my labels simple. And we know this is going to be 100%. Well, turns out 30% are icy delay. We know that one. That's the easiest one. Well, if that's 30%, then not ice delay is 70%. We can write this small right here. Okay, so if a flight is delayed because of icy weather, so we're looking at the icy delays, there's a 10% chance it'll be delayed because of mechanical. Oh, so ice delay mechanical, this gets a 0.10. This is going to get 1 minus 0.1, which is 0.90. If I multiply, this is 0.03, and this is 0.27. And this need to add up to this, and they do in this case. We feel pretty good about this. If a flight is not delayed because of icy weather, so no icy delay, there's a 5% chance that it'll have a mechanical problem. So mechanical delay. So this is 0.05. There's the 5%. And if that's 0.05, 1 minus that is 0.95. When I multiply these, this becomes 0.035. And I'll check that out real quickly. 0.7 times 0.05, 0.035, and then 0.7 times 0.95, 0.665. And I add these and I get 0.7. So 0.03 plus 0.035 is 0.065. And then 0.27 times 0.665. Oops, not times, plus 0.27 plus 0.665 is 0.935. And if I've done everything correctly, these two values should sum up to one whole. So let's just make sure, because that way we know we're doing the right thing, plus 935, and everything adds up to one whole. So what's our actual question? What is the probability that the flight selected will have at least one of the two types of delays? Well, where are my delays? Ice delay and mechanical delay. So this is where we really have to be careful, because we're going to go, all right, we want to add up two probabilities. So we want to go the probability of A plus the probability of B minus the probability of A and B, because we can't just add them without subtracting the intersection. So we have 0.30 plus 0.065 minus, there's my intersection, 0.03. So when I do this, 0.3 plus 0.065 minus 0.03. And I end up getting 0.335 as my answer. Now, the reason I had to subtract it out is because this 0.03 was counted twice. It was counted right here, and it was counted right there. Now, there is another way to have done this. We could have added up just the marginals. The 0.27 plus this would have given me the same answer. But I think it makes more sense to, the joints. Instead of doing the joints or the conditional, I think it makes sense to add the two marginals and subtract out the intersection, because that's our formula. Because the probability of A union B equals the probability of A plus the probability of B minus the intersection. So I think it makes more sense to use the formula rather than adding these two or adding these three together, but you could have. All right, a survey was administered to parents of high school students in a certain state to see if the parents thought the students' academic needs were being met. To select a sample, the parents were divided into two groups. One group of parents who live in cities with populations of more than 100,000, and other group of parents who live in cities of populations with less than or equal to 100,000. So we have two groups. Greater than 100K and less than 100K. But the two groups is an important thing, and you'll see why in a moment. A random sample of 100 parents from each group was taken. So within this group, we took a sample of 100 parents, and within this group, we took a random sample of 100 parents. Which of the following statements of the sample of 200 parents is true? Well, first off, because I divided it into groups, it can't be a random sample. And matter of fact, all it can be is a stratified or a cluster. All right. So convenience is gone, systematic is gone. And so we're left with stratified and cluster. Now we divided them into groups and then we took a random sample within the group. That is a stratified, all right? Because we made sure each group was represented. In a cluster, we select one group or more and then survey everybody in the group. We didn't survey everybody in the group. We only surveyed part of it. We did a random sample within the group. The random sample within the group tells me it's stratified. Again, if it had been a cluster, we would select one of the two groups and we'd survey everybody in those groups. And of course, the groups needed to look alike. Number 10, a popular computer card game keeps track of the number of games played and the number of games won on a computer. The cards are shuffled before each game, so the outcome of the game is independent from one game to the next and is based on the skill of the player. Let X represent the number of games that have been won out of 100 games. Under which of the following conditions would a binomial random variable? Well, to be a binomial random variable, it has to be a Bernoulli trial. And that means our probabilities have to be fixed. They can't be changed. They need to be independent. They told us they were independent. That's good. And to be a binomial, we have a fixed number of trials. All right, so the number of trials isn't changing. We're just going to set it up at the beginning and say, hey, we're going to do it this many times. All games are played by the same player whose skill improved. If skill improved, then the probability changed because the probability got better each game. So that's not it. We have to have the same probability. A group of 5 players of different skill levels. No, we have to have the same probability. Probabilities must be the same. A group of players of different skill levels were allowed until they had lost 3 games. And it's like, no, you're playing until you lost 3 games. That makes it a geometric, but this also says they have different skill levels and the probabilities have to be the same. 2 players of equal skill, that's good. The probabilities are the same. Each played 1 game a day for 50 days and their skill levels did not change. Probabilities did not change. Skill levels, probabilities are equal, and we have a specific number of trials. That's sounding pretty good. 2 players at different skill levels until a game was lost. First off, you have different skill levels. That's bad. Needed the same probabilities, but you're also continuing until a game was lost, which means you didn't have a fixed number of trials. And to be a binomial, you have to be a fixed number of trials. So E is bad. The only choice that works is D. Thank you.